Next, we are going to discuss the learning part of support vector machines. So we just discussed the principle, support vector machines, and max margin hyperplanes. Now we dive into learning, and in the next section we will discuss the kernel trick, which will boost support vector machines to really strong classifiers. So how do we learn support vector machines? And as often the answer is in machine learning, well, by optimization. Formulate the learning problem as optimization problem and solve this optimization problem. And now we will do some exercises. We will start with a rather direct formulation, which will be problematic though. And then we will tackle this problem from different angles and transform it until we end up with a convex optimization problem. So this means we can solve it and guarantee a globally optimal solution. And then, so first we will start with support vector machines for linearly separable data sets. And then in the end, we will generalize this to non-linearly separable data sets, so to arbitrary data sets. And a big deal about this whole exercise is essentially to dive into this machine learning philosophy to formulate your learning algorithms as optimization problems. So this is not only about support vector machines, but by reconsidering our optimization problem again and again and tackling it from different angles, we'll see the development phase of machine learning algorithms. So there's something to learn here. So let's get started, and we will assume linearly separable data for now, and we will fix this later. So for now, we assume that there is a data set and we can strictly separate it with a separating hyperplane. And the goal is to find the max margin hyperplane. So the setting, we have some data points. So these data points here, features and labels, and the labels are encoded with +1 and -1 for positive and negative class respectively. And we are working with hyperplanes, so affine function W transpose times X plus B, and we take the sign. So we classify +1 if the affine function is large equal 0 and -1 otherwise. So this is the setting. And now let's start with our first optimization problem. So max margin hyperplane. So the margin again was the minimum distance between our hyperplane and any data point. So let's just specify, well, Euclidean distance of data point xi to our hyperplane specified by w and b. Let's call this just dwb xi. And now the margin is the minimum over all our training points, and we'll want to maximize this. So very direct formulation. So this is correct, but actually if you provide this to an optimizer, this is too abstract for an optimizer. So the optimizer doesn't even know what Euclidean distance means, so this is very symbolic. So this is correct, but actually not really useful for current optimizers. Maybe at some point in the future we'll be able to formulate it like this, and the optimizer will do all the work, but still now we'll do the work by hand essentially. So we need to formulate our optimization problem a bit more explicitly. So we need to dive into geometry essentially. So for this, to reformulate our optimization problem, let's do a short recap of geometry, and in particular the distance between point and hyperplane. So here is our hyperplane specified by the normal vector W. And now recall the points which fulfill W transpose to X minus B equals 0. These points are building up this hyperplane, where the points where W transpose to X minus B larger equals 0, this is this half space. And from smaller 0, this is this half space. So hyperplane equals 0, larger equals 0, half space, and minus smaller than 0, this half space. And now recall if we have a point, so this is from essentially basic geometry classes in high school usually. If we have a point in the positive hyperplane, positive half space, then the distance between our hyperplane and this point is given as, well, W transpose X minus B. So this is this equation which specifies our hyperplane. W transpose times X minus B divided by the norm. This is the Euclidean distance between hyperplane and this point in the positive half space. And essentially we have the same formula if the point is in the negative half space, but essentially just it's a signed distance. So note this minus sign here. So if the point is on this side, then it's still the same formula, W transposed X minus B over the norm divided by the norm of W, but now it's a signed distance. So here's a minus. Useful for classification, so we need to look at the signed distance. So if the signed distance is negative, we are here, and if the signed distance is positive, we are in the positive half space. So now, well, W transposed X minus B is the signed distance between xi and the hyperplane. But now you recall that our label yi is +1 for positive examples and -1 for negative examples. So if we have a separating hyperplane, and then if we multiply the signed distance by the label, then this actually becomes exactly the distance. So this becomes exactly the distance if we are working already with a separating hyperplane. So, or in an optimal solution, this will be the correct, so non-signed or non-negative distance due to the multiplication by this label yi. So essentially this is now equivalent to the first problem. Maximize the minimum distance to any training point. So this is the max margin formulation. So this is equivalent to problem 1, and now we formalize this mathematically. So this is a valid optimization problem, and we could actually, for example, use gradient descent and try to solve this. Unfortunately, however, so we have this minimum over all the training examples, and we also have this division by the norm of our normal vector, and therefore this problem is a valid optimization problem, but it's not convex, unfortunately. So in particular, we cannot guarantee a global optimal solution. So let's try something else, because I promise you in the end we will come up with a convex solution which we can solve globally optimal. So let's try something else, and let's work with these margins. So here we have our hyperplane. So this is not the max margin hyperplane, but any separating hyperplane. So this is W transposed X minus B equals 0. This is the hyperplane. And now we introduce two hyperplanes, the so-called margin hyperplanes, specified by Wx minus B equals -1 and Wx minus B equals +1. And this first one is now this guy here, this so-called negative margin hyperplane, which is slightly shifted into the negative half space. And we have this guy, Wx minus B equals 1 +1, slightly shifted in the positive half space. So we call these the margin hyperplanes. And similarly as we computed the distance of a point to the separating hyperplane, it can be easily shown that the margin, so the distance between the central hyperplane and the margin hyperplanes is, so this margin D is 1 over the norm of our separating hyperplane. So if we now scale W and B by some positive constant, then we actually we scale down the margin D. So if we scale W and B times 100, we would scale down the margin by 100 because it's reciprocal to the norm of the normal vector. So this means if we already start with a separating hyperplane, then we can always achieve the following. So if we start with a separating hyperplane, then by essentially just scaling up W and B, we can move these margin hyperplanes closer and closer and closer and closer to the separating hyperplane. So at some point, by just scaling up W and B, we would also fulfill this constraint. So this constraint, Wx minus B small equal -1, which means all the negative points lie on this side of this negative margin hyperplane here. And also we can fulfill a similar constraint for the positive points, W transposed X minus B larger equal 1, so which means all the positive points lie strictly, not strictly, lie on this side of this margin hyperplane. And we can always achieve these two constraints essentially just by scaling up W and B, because we can move essentially the margin hyperplanes closer and closer and closer to the separating hyperplane. So now we can use this to formulate our optimization problem. So we want to work with this constraint, and we enforce these two constraints for the negative and the positive points. So all the negative points must now be on the correct side of the negative margin of the negative margin hyperplane, wx minus b smaller equal 1, and all the positive points must satisfy wx minus b larger equal 1. This look like different constraints, but actually again by multiplying with our label. So for positive examples, this is +1. For negative examples, this is -1. So if we multiply a -1 here, then essentially this constraint turns to this constraint. And this essentially multiplying a +1 here for the positive points doesn't change anything. So these two constraints, by just multiplying with yi, so +1 for positive points, -1 for negative points, these two constraints become the same constraint. So all points must now satisfy this constraint here, and we call this the margin constraint. So it's now the same form for negative and positive points, essentially just by correcting negative points with a -1 here. Then this constraint turns into this constraint. So now we have essentially just constraints for each data point. So we have uppercase N data points, and all the data points need to fulfill this margin constraint. And additionally, we saw that the distance between our separating hyperplane and either of the margin hyperplanes, so again, this in the guy in the middle is our separating hyperplanes, and these are the margin hyperplanes, and we saw that the distance is 1 over the norm of W. So we have that the distance is 1 over the norm of W. And this leads to the following optimization problem. Maximize our hyperplane, so with respect to the parameters of our hyperplane, 1 over W. So this is the margin, subject to that all the margin constraints are fulfilled. So essentially this is now equivalent to the previous problem. So this is now just a slightly different derivation, and it's solving. So an optimal solution here will be the maximum margin hyperplane. So unfortunately, this is still not convex due to the objective term. So since 1 over the norm of W is not convex. However, we can easily fix this because maximizing 1 over W is equivalent to minimizing the norm of W. So we change 1 over W to W, the norm of W, and maximization by minimization. And now we also do a minor tweak. So instead of minimizing the norm, we can also minimize the quadratic norm, or also like have this cosmetic 1 over 2. So it doesn't really matter if we minimize the norm or the quadratic norm. So the quadratic function is monotonous. So these two are essentially the same, so equivalent to each other. But the second one is differentiable and leads to a nicer optimization problem. And therefore we arrive now at this fourth optimization problem, which is equivalent to the previous optimization problems, which is minimize with respect to the parameters of our hyperplane a half of the quadratic norm of our normal vector, subject to these margin constraints here. And now we have good news. So this is now a formulation of the max margin hyperplane where we have a quadratic objective. So this is a quadratic objective in the parameters. We have linear constraints. So these are just, if you look at this, these are affine, it's an affine function. So therefore this is linear in W and B. So these are linear constraints. And this is just a special case of a so-called quadratic program. And the good news now, this is convex, and there exist standard solvers to solve this problem. So essentially you can just formulate this problem and give it to a standard solver for a quadratic program, and you get an optimal solution out of there. However, you don't even need to use a standard solver because there are tons of implementations for support vector machines, so specialized solvers is essentially for this optimization problem. So essentially you can just use ready software and train your support vector machines. But it's a good exercise to see how we reformulate these optimization problems, and the first formulation is often not the best way to actually solve it in practice. So great, mission accomplished. But wait, so we always assumed linearly separable data. So what if this doesn't happen? So what if our data is not linearly separable? And this is actually a pretty strong assumption to assume that our data is linearly separable. So what do we do in this case? So in order to answer this question, let's look again at our margin constraints, yi times w transposed xi minus b larger equal to 1. So here again we have our separating hyperplane and the positive margin hyperplane. Now let's look at a point, which a positive point, so a point with positive label, and let's consider this point and say it's strictly in the positive half space. So it fulfills the margin constraint even with strict inequality, so it's strictly larger than 1. So and we are very happy with this point, so it's correctly classified and it fulfills our margin constraint. So very happy with this point, a good point. So if the point now moves closer and maybe even onto our margin hyperplane, then the margin constraint will be fulfilled with equality. So now so w transposed xi minus b is now exactly 1 rather than larger than 1, strictly larger than 1. So this is still a good point. So still this fulfills our constraint and we are still happy with this point, but it's already getting close. Now say if oopsie, this point moves over the margin hyperplane and now the constraint is violated. So this constraint is now violated and now w transposed xi minus b is now smaller than 1. So now the constraint is violated, but it could still be worse because we're still classifying this point correctly, but it violates our constraint in the optimization problem. So it could even be worse that we even move over our over our decision boundary. Now this constraint is actually violated smaller than 1. If we go back, essentially the only difference, so very happy, happy, unhappy, and very unhappy, the only difference was always just how much this affine function deviates from our constraint. So here it was strictly larger than our constraint, exact satisfaction of the constraint, slight violation of the constraint, and very strong violation. So essentially this gives us a key to relax our constraint and work with data which is non-linearly separable. So since in non-separable data, we will never be able to achieve all the margin constraints. So if the data points are overlapping, then there won't exist a separating hyperplane, and the optimization problem will be infeasible. So this original optimization problem will be infeasible, and we will not find a separating hyperplane. And so therefore we have to relax our constraints. And as we just saw in the previous example, we are more happy the less a constraint is violated. And we can now express this happiness with so-called slack variables. So we can relax now our constraints. So these are the margin constraints, and we can now relax them by discounting them with a so-called slack variable xi. So we have one slack variable xi per constraint, and therefore per data point, because we have one constraint per data point, and we relax these margin constraints with this xi, and xi should be larger than 0. Since if xi were allowed also to be smaller than 0, then we would actually also pay some benefits for these points, but we don't want it. We just want to have that these constraints are fulfilled ideally, but we don't we don't care how much. So if a point is like really up there, then we don't want to pay more than this point or even this point. So therefore, the slack variables need to be positive, and they are essentially this discount for our margin constraints. So these are our margin constraints, and we relax them with slack variables xi. And however, we don't want too many constraints to be violated. And if they are violated, we don't want them to be violated by much. So we want the xi's to be small. And since we are dealing with optimization, the immediate idea is, well, we can include them in our optimization problem and penalize them. So we include them in our objective and penalize them. So to this end, let this boldface xi be the vector containing all the xi's. So all the xi's for all the samples and margin constraints. And then we come up with a new formulation of the support vector machine, and this is called support vector machine with soft margin. So the original one was the hard margin support vector machine, and now we have a soft margin. So we are a bit relaxeder now. And essentially everything which is in black here is the original hard margin formulation, and everything which is in green now is new. So we relax our margin constraints with the slack variables xi. We ask that the xi's are positive, and now we penalize the sum. We want to minimize also the sum of all these slack variables. And essentially now we need to trade off the norm of our hyperplane, of the normal vector of our hyperplane, and the sum of slacks. And this is governed by this trade-off parameter z. So hyperparameter z trades off the norm of our parameter vector and the sum of slacks. So if z becomes infinite, goes towards infinity, then essentially we are going back to the hard margin, because then this means we are really annoyed if any of these constraints is now violated. So don't violate any of these constraints. You will pay infinite penalty if you violate any of these. And in general, so like this is now a relaxed version, the soft margin, the support vector machine with soft margin formulation. And well, this C trade-off parameter is now a hyperparameter, and we can, for example, select this with cross-validation. So for example, on a separate validation set, we've discussed this in the last lecture. So if you need a refresher, check out the last lecture where we discussed a validation set. Anyhow, so this is still a quadratic program, and there are still solvers which solve this problem for you. Okay, so this essentially already concludes the section, but here's a little exercise for you. So this is again the soft margin formulation as we saw on the previous slide, and now I give you a different formulation, a different optimization problem, namely minimize the norm of the W's plus C times the sum over all samples. And now we have this function here. This is the maximum of 1 minus yi w transpose xi minus b and 0. So essentially this maximum clips this function at 0. So if this function is smaller than 0, then essentially the maximum picks 0, and therefore so we clip at 0. So if this is larger than 0, then the maximum will pick this, and otherwise it will pick this. So this will introduce essentially a hinge, and this is often called a hinge loss. And now I claim these two optimization problems, they are equivalent. They are the same essentially. And I want to ask you, can you see why they're equivalent? And a little help maybe is think about points which fulfill their margin constraints, so where they are larger than, where this left-hand side is larger than 1. Think about if this happens in an optimal solution, what will be the xi then? So if this is anyway fulfilled, what will be xi then? And if this is not fulfilled, how will xi then be given? And essentially if you plug in this in each other, then you can essentially show that these two are equivalent. And I would like you to think a bit about this. So the second thing is still convex, and it doesn't have any constraints, which is good, but it's not a quadratic program anymore. So it's like in this first case. Here are some examples demonstrating a bit the effect of the trade-off parameter C. So in this first example, we have non-linearly, data which is not linearly separable, and we play a bit around with this C parameter. We see that in this case, there is not too much effect, so the hyperplane moves a bit. So here we see with this point it moves a bit, but here it seems to be not too sensitive. And here we also check a linearly separable data set, and we play with this trade-off parameter. So Z is here very small, which means we don't really care too much about the slacks, but more about a small norm. And we see that this actually is not yielding the hard margin. So since the hyperplane is very close to this red point, and only if C becomes rather large, then we're essentially going back to this really diplomatic hard margin hyperplane. So now this really concludes this section. So now we've succeeded in formulating the support vector machine as a convex optimization problem. And a big deal of this exercise was to see how this generally works, this method development in machine learning works, and that we have to play around with different formulations. So knowing tricks or knowing optimization and optimization tricks helps a lot in formulating a problem. And in this final formulation, essentially the geometry was not immediately visible anymore. So, but essentially doing this whole derivation from geometric standpoints and ending up with this final definition of our support vector machine, we came up with this recipe. So we minimized the norm of our parameter vector subject to these margin constraints, and we saw that this is equivalent to maximizing the margin. So this form is very typical in max margin formulations, and minimized norm plus margin constraints. This you will be able to recognize this from now on. So it's not this max margin formulation not only pops up in support vector machines, but often in machine learning literature. So if you see this once, then you will be able to recognize this in the future. And finally, we introduced these slack variables, which essentially allowed us to relax these margin constraints, and therefore now we can apply these support vector machines with the soft margin to arbitrary data sets, so also for data sets which are not linearly separable.